going to be constructing confidence intervals for slope and also doing t-tests of slope. And so that is giving us our best estimate of what we think the true slope might be. And we know that this formula from the formula sheet, that is the general formula for any confidence interval. And in our situation, we're going to, for our statistic, we'll be using our sample slope, and that would be RB. And then what we're going to do is get our critical value, and we will be using critical T values. And so we're going to need to know the degrees of freedom. But in our situation, because slope involves both y and x, our degrees of freedom are going to be n minus 2. So that's going to be very important that you make it a little bit more conservative by decreasing your degrees of freedom by 2. Instead of by 1, you're just decreasing by 2. And that is because in slope, we're looking at change in y over change in x. And so that's why, to be unbiased, we need to do that. Now, then the last thing is the standard error of the slope, which hopefully you'll have an output. However, on your mini quiz, you're going to have to calculate yourself. But that's fine because you have the formula for how to do that, which is right there and also on your formula sheet. So it really just involves getting the standard deviation for the residuals and the standard deviation of x, and then putting it into that formula. So let's construct the 95% confidence interval for the slope of the population regression line for our helicopter data. In the previous video, we looked at the raw data and we checked liner. Okay, we checked that it was linear, that it was independent, nearly normal, equivariant, scatter, and random. And since the conditions were met, we are going to be doing a confidence interval. What kind of confidence interval are we going to be doing? We are doing a t-interval for the slope of the least squares regression line. So make sure you're saying what you're going to be using, and that way we'll be able to find it on our calculator. So we are doing a t-interval for slope of linear regression line. Okay, and because we are doing slope, we need to be mindful that our degrees of freedom will be n minus 2, not n minus 1. There were 70 trials. Remember, n was equal to 70 trials. So we are going to have 70 minus 2. We are going to have 68 degrees of freedom. And what alpha level are we going to be using? If it's 95, our alpha is 0.05. That's my favorite anyway. So we need to get our statistic. We're going to plus or minus our critical t value and our standard error for our slope. And so let's see what we had for output. We had for output for beta, on the other page, we had that the slope of our helicopter, they predicted it as 0.0057244. Look back at page before and you can see that. And if you look at the output, the standard error of the slope, they had that as 0.002018. Now the units of these were seconds per centimeter and seconds per centimeter. Those were the units. Critical t value. Critical t for an alpha of 0.05 divided by 2, because it's a confidence interval, with degrees of freedom of 68. If I do inverse t on my calculator with 0.025 comma 68, the calculator is going to spit out 1.995. So now let's take these three numbers and put them together in the way that we would for a confidence interval. And so we are going to take our 0.0057244, add and subtract the critical t of 1.995, and then our standard error slope 0.000218. Whoops, I wrote that. I forgot a zero. Let me rewrite this. I think like Smartboard just seems to be, when I write in this one spot, it makes it really crooked looking. Okay. And then when we punch that into the calculator, we get a lower value of 0.005322. We get an upper value of 0.00613. And what symbol do we want in the middle? We want the population symbol. Make sure you do the parameter symbol here. So that is a beta, because we're estimating that true value. So now let's write our conclusion. So with 95% confidence, the interval from 0.005322 to 0.00613. Now I probably should put units on this of seconds per centimeter. Estimates the true slope of the helicopter drop height and flight time model. If I had used the word versus, I would have had to put the flight time first. And then if I'd forgotten to put my units, I could always say in seconds per centimeter at the end of it. Okay, so that was a confidence interval. Now we'll do the same thing with, same idea with the test. So now we're going to do a t-test for the slope of the least squared regression line. Here's our output again. So in this case, we have to go through and do our test statistic. And you can see how it looks like what we've been doing before. And then we do need to write our hypotheses. And so if you look at these are our alternative hypotheses. And so this one would be if we were looking for a positive slope, if we were trying to find evidence of a positive slope. Are we trying to find evidence of a negative slope? Or are we just trying to find evidence of any slope at all? Slope. And so if we are looking for just any slope, that's when we have both tails. And the output here, these p-values, are for the two-tailed cases. Two-tailed cases. So they are looking at both ways. And so you can see that the p-value for this is extremely small, giving us evidence of the slope being, that there being a slope. So again, we have that the conditions are met. So liner was checked. We saw that the conditions are met. So what are we going to do? We're going to do a t-test for the slope of the least squares regression line. Okay, so we're going to be doing that. And again, degrees of freedom is going to be important, but we don't actually have to test, we don't have to find the, we don't have to punch it all in because they actually have all of this information in the output. For example, right here, that's the t-test statistic. So if I had done t equals, and I had done my sample value minus my hypothesized, this coming from the null, over my standard error of my slope, that would have come out as 28.37. That would have been my t. And then my probability of my t being greater than a 28.37 equals something, then doubled. Well, it's obviously going to be 0 because like when you have multiplied that number by 2, you still have 0. And then that's looking for evidence against the null and alternate hypotheses. So I really do need to write those. My null would be that my slope is, there's no positive or negative, no evidence of a slope. So this is when we're saying the null will always be this, which is no evidence, or not enough evidence of a slope. And then my alternate hypothesis will be whatever I'm checking, positive, negative, but in this case I'm checking just, is there any evidence of any kind of a slope at all? And so then I get that right there. And so that means that, recall up here, this right here, this part of the equation will always be 0 because the null is always going to be testing 0 for this. So I'll write my conclusion based on this p-value. Okay, so since the p-value of 0 is less than alpha equal 0.05, we reject the null hypothesis and there is significant evidence of a, now what is this concluding here? Some kind of a linear relationship, not necessarily positive or negative. There is evidence of a linear relationship between drop height in centimeters and flight time. If I had used verses, I would have put the flight time first. And so that, for our model, that's what we're finding. So the null is not evidence of a linear relationship. The alternate is either going to be evidence of a positive linear relationship, evidence of a negative linear relationship, or just evidence of a linear relationship. So now we've got this data here. I'm going to run through this, and then in the next video I do an example where I do everything, which includes, in the next example, it'll also show you how to use a calculator. But in this example here, we have this raw data. It's been put into the calculator, and these graphs have been generated. And we also have output, which means we have a lot of the information already. And so we are going to look at this to decide if this is meeting. Okay, this, to me, the slope here may be moderate, but it does look like it is going up for the strength. So form would be linear, direction is positive, strength is moderate. So that is satisfying the L. Okay, then this is our graph of our residuals. Don't see any patterns developing here. It does look like chance scatter, equivariant scatter. So that is satisfying the E, that it is equivariant scatter. So that's good. And then over here, I don't have the histogram, but I have the very important normal probability plot. Probability plot. And this is of the residuals. And that is looking very straight. So that is satisfying our N condition. So I have the L, the E, and the N. Let's verify that this was random. Okay, so we have random. They had a bunch of babies. They snapped rubber bands on the sole of their feet and caused them to cry. They don't really say that it's a simple random sample, but there's no real evidence that it's not. But I think the results will be good for these particular babies. Infants. And I would say that they did a sample of, let's see, how many babies did they have here? 38 babies. So I would say that 38 is less than or equal to 10% of N, because there's definitely more than 380 babies. Okay, so that means that we have our conditions met. So what are we going to do? We're trying to prove here, is there evidence of a positive linear relationship? They're wanting us to do a test. They're not asking us for what is the window for this relationship. What is the window of the slopes? They're asking us to test, does there appear to be evidence of a positive linear relationship? So we are going to do a t-test for slope of the linear regression line. And so let's write down what we're going to be testing here. We're going to be testing the null hypothesis of our slope. Notice the population symbol not being a linear regression, evidence of a linear regression line, versus the alternative. And they specifically want us to have a positive slope for this linear regression line. So looking for this positive linear relationship. Okay, so what's our degrees of freedom? There were 38 babies. So if n equals 38, we're going to go n minus 2. That's going to be 36 degrees of freedom. My alpha is not provided to me, but I will do alpha equal 0.05. And so now let's go up and figure this stuff out. Now, my t-test statistic, I would take my slope and I would divide by, so let's take that value from the output. I can see that the slope is 1.4929. I see that right here. I see my standard error for the slope right here. Okay, so let me write that down. Minus 0, because remember that comes from the null hypothesis, over, and now let's put the standard error right here, 0.4870. And coincidentally, when you punch that in the calculator, you're going to get that t that's actually provided on the output of 3.07. When you do the probability of your t being greater than a 3.07, because we're on this curve here and 0 is in the middle and we're looking for 0.7, we're looking for that. The output actually shows the p double value, which equals 0.004. So I know that half of that 0.004 divided by 2 is going to be 0.002. And so that's going to be this number right here. But I could have also have used my calculator, and I could do, if I wanted to, I could have done TCDF. I'm writing it in red because like you wouldn't write this calculator speak on your paper, but if you wanted to check it on your calculator, 3.07 comma some big number, writing right here, it always makes it really crooked looking, and then degrees of freedom of 36, and then that would come out with something close to this 0.002. But next video I'll do the calculator. But since the p-value of 0.002 is less than alpha equal 0.05, we reject the null. Remember, the null is that there's no evidence of a linear relationship. So we're going to reject the null hypothesis. And there is significant evidence of a positive, because that's what my alternative hypothesis was, positive linear relationship of, and then this is between crying and IQ, or crying intensity, crying time, measured the intensity. So crying intensity and later IQ scores. Okay, so the next video I'll also show the calculator and how you can actually do all of this really quickly with a calculator if you have the data in the calculator.